Hi, so we continue with ergodic theory, and in the last lectures we talked about the definition of ergodicity, invariant events, uh, measure preserving implications, and we talked about ergodicity also in connection with mixing and the IID case. In this lecture we're going to use these definitions and give some results concerning ergodic measures. So the main result actually of ergodic theory is given in this lecture, which is Birkhoff's ergodic theorem. So this is perhaps the most important theorem of this set of lectures, and we are going to motivate it through two different visions. So the first is connected to what we mentioned before, that somehow ergodicity is is an extreme case, or the weakest possible form of independence, so to say, we can have in a measure here. So mixing is weaker than IID and ergodic is weaker than mixing. And so we could look at the theorems we know for IID and see if they hold for mixing and ergodic measures. So Birkhoff's ergodic theorem somehow extends the law of large numbers that holds for IID random variables all the way down to ergodic measures. So this is one possible way to see Birkhoff's ergodic theorem. Now, another interpretation comes from physics, and it's not easy to explain briefly what is meant here, but I will give a very brief introduction to statistical mechanics. So imagine you have a system, for example, a box with interacting particles inside. So these particles navigate, travel, collide with the boundary of the box, and maybe collide among themselves, interact in strange ways. And the number of particles is big enough that you don't want to do any ordinary differential equation with these many variables and try to solve it. Instead, what you want to do is understand some macroscopic properties of the system without having to solve the microscopic equations. So is it even possible to do? I mean, from an empirical point of view, of course it's possible. We look at materials that are composed of enormous amount of atoms, but we can understand them with very few observations, like what's their conductancy of heat, what's their temperature, pressure. So there are few variables that somehow summarize everything that's going on inside the system. So it sounds like it's possible to do this reduction of complexity. Now, Birkhoff's ergodic theorem can be understood as one of the steps to do the simplification. So going from this complex system and simplifying to a few variables like pressure, temperature, number of particles, and so on, like a simple set of observables. This is what's studied in thermodynamics and thermostatics. So, but to justify this transition, we have to do several steps. And this is a road or a plan, a long-term vision. And some of these steps have been done rigorously and some of them are still to be done. And we are going to prove this step, the middle step in this procedure, which is Birkhoff's ergodic theorem. So what are these steps? So you take a system that is very complex and you find mu that's invariant with respect to the dynamics that you defined on these particles. This is not easy to do, but it's also not crazy complicated. This is something we can sit down and do. Now we have an invariant measure that is invariant with respect to the dynamics. We would like to be able to only look at this measure and tell things about this system. The problem is the system could be in a certain energy, for example, and this measure, it has some points with bigger energy, smaller energy, and we know that energy is a conserved quantity, so we actually should restrict this measure to a level of energy. Like if this system that we started with has energy E, we should not look at the whole invariant measure, we should just look at the measure restricted or conditioned on having the right energy. And what if it also has another conserved quantity, like the number of particles? I mean, we should focus on all the quantities that are equal to our system. Now, if we stop doing this, if we do this for all the conserved quantities, there are no more conserved quantities. That's what the physicists would say. Now, this is ergodic with respect to mu, to phi. And if you have an ergodic measure, so the second step is taking care of the conserved quantities. The third step is easy, it's Birkhoff. So this is what we're going to do today. It's not that easy, but it's it's doable. And the fourth step is studying the measure mu itself, mu restricted, like the one conserved. This is also a big question, right? So this is okay. This is a big open problem in dynamical systems. This is okay, and this is can be a big open problem or not in probability theory, depending on whether or not the system you started with is complicated and the measure is complicated. But if you fix all this, then you have thermodynamics or thermostatics. So you can, for example, explain all that this theory explains in very easy ways. So you can explain phase transitions, for example, why the water boils down at 100 degrees and why there are strange phases of water, several different types of ice, things like this. You can explain metastability. You can explain glassy behavior, why things behave like a glass, which is a very strange type of phase. So there's so many things complex in nature because it's dealing with so many particles that if you understand all these steps, you could actually just translate to this simple set of parameters. But this is a roadmap that has been fully done for some simple models and are yet to be done for more complex models. And I'm not, of course, gonna give more details on that. We're gonna jump straight into Birkhoff's ergodic theorem. So imagine that we have a application phi. So phi is going from S to S. So let's already state the theorem, right? Don't need more introductions. So theorem. So this is a modified version of Birkhoff's theorem. You have an application phi, which is invariant with respect to P. So that means P is P phi minus 1. Then for every x, can be understood as a measurement. So for example, here, x could be the average speed of particles or the average distance between particles. So these are things that um, or these are things that usually can be observed macroscopically as well. So you have this measurement that brings you to the real line, and you'd like to integrate x along time. So here this belongs to L1. This is an hypothesis because we want to integrate. Integrate along time means this. You take the time average as time goes on. So this is what you have your state space S. You start at omega and you keep applying x, sorry, phi, apply phi, apply phi, and you measure x at all this orbit and you take the average. And this converges almost surely and in L1 to the expectation of x given the invariant sigma algebra. So first an observation, I is the set of all events such that A is invariant, and this is a sigma algebra, or sigma field if you want. So this is not difficult to check. We are going to state the original Birkhoff theorem that has no conditional expectations in the end. So as a corollary, if P is ergodic, then we have this average. Of course, the result's still true, right? So this converges almost surely to the expectation of x given I in L1. But if P is ergodic, then for every A in I, we have the probability of A is either 0 or 1. And since this is all that can happen, every event x or random variable x is independent of I. So every event is independent of an event that has probability 0. Every event is independent of an event that has probability 1. So x is going to be actually independent of I. So the conditional expectation is just the expectation. So this is the more traditional way to state Birkhoff's theorem. If the measure is ergodic, time averages converge to average with respect to the ergodic measure. Now, how this relates to the physical, to the two interpretations we gave. So first, this clearly can be seen as a law of large numbers, but now we are not using the usual IID thing. We are taking things that are definitely possible to be dependent, potentially dependent, and this is converging just like the law of large numbers, especially in this case, right? If it's ergodic, which is actually what we are, the analogy we did above, then the sum, the average will converge to the expectation, just like in the law of large numbers, almost surely, and in L1. Now, this interpretation is clear. This interpretation is a bit less clear. So what we did here was to find an invariant measure. This is easy to do. We found the invariant, the conserved quantities. We fixed them. So we found a slice of this measure that is still invariant. But now not only that, we cannot slice it further, so it's ergodic. This, together with Birkhoff's theorem, says that the space, the time averages converge to space averages. So my mu x, the expectation of x with respect to mu. So what is the physical interpretation of this? We let the system evolve for a long time, and we make a measurement over time, and this will be just an integral that we can calculate if we know mu. So if we studied mu properly, we can just calculate these integrals. So this is how this fits here. And this time average make a lot of sense because these systems evolve very fast. So the time for a particle here to cross the interparticle distance is of the order of microseconds, even less, nanoseconds. So this is extremely fast. So every time you look at a gas, you're actually taking just an average. So this is the motivation behind the physical part. And now let's go to the proof. And the proof is a bit involved. First have this lemma, which sometimes called the Ergodic Maximum, the maximum ergodic lemma. So we defined x to be this random variable sitting here, right? And we're going to define now xj as usual. Its interpretation is very similar to what we've done in the case of the canonical projections. X0 is of course just 0, and xj plus 1 is xj imposed phi. So in the end, xj can be written as just x of phi j of omega. Okay, so xj is this composition. When we look at Birkhoff in the light of the shift, if s is equal to s to the n or to the z, and this phi is just the shift, and x0 is the canonical projection in the 0th coordinate, then the xj is going to be the canonical coordinate j. So the analogy is perfect. So now in this lemma, we define this xj's, but also define the sj, which is going to be the sum of the j first coordinates. Sorry, let's call it sk. And we also define the maximum, mk, the maximum of the sums, s1, s2, until sk. Now here, strange that the maximum is going to include 0. So it's a different maximum that what we have seen up to now. We force 0 to be there. So this is clearly non-negative. And what this lemma tells is that if phi is invariant, meaning p equals p phi minus 1, then the expectation of x at the event mk larger than 0 is larger or equal to 0, which for me is quite a surprising statement. So we have x. There is no reason to think that x has positive or non-negative expectation. Could be that the expectation of x is negative. We have this x and we iterate it, and if the maximum is larger than 0 for any k, then we all of a sudden have some information about x0. This is x0, right? And we have an information that its expectation at this event is non-negative. So this is the lemma. If the statement is not very intuitive, the proof is even less. So actually the proof is gonna be a bit more obscure. The intuition, at least in the beginning, in the statement is that, okay, if you're moving the maximum to be positive, you're moving everything up, so maybe x also moves up and is non-negative. But the proof is kind of obscure. So if j is smaller or equal to k, then the maximum is clearly larger or equal than the sum, right? Because the maximum includes this sum in its definition. Now, not only that, but we're going to apply this holds for every omega. But we're not going to use for any omega, we're going to use for phi of omega. Why is that? Because now we sum x on both sides, and you get x plus mk of phi omega bigger or equal to x plus sj of phi omega. So this is, of course, true. And the interesting thing is that here we obtained something that we know. So what is Sj? Sj is the sum for x0 until xj minus 1. When we apply phi, we increase the indices of everyone. So now this is summing from x1 to xj, not xj minus 1 anymore, xj. So if we sum now x0, we get exactly sj plus 1 of omega. So that's why we started with having this phi here. Now, simple algebra, x omega is larger or equal than sj plus 1 of omega minus mk of phi of omega. And this for every j smaller or equal than k, right? So what's very interesting here is that if this is true for every j, we can take the maximum, right? So x, this is pointwise, right? This is also for every omega. So now this is also bigger or equal than the maximum for S1, S2, and so on to Sk. Minus, here there's no j, so this doesn't change when you take the maximum. And this now looks a lot like m again. It's not m, but it's almost m. That's what we want to obtain in the end. So now we can take the expectation in the lemma, right? This expectation of x on the event mk larger than 0. And you see that mk larger than 0 is very convenient, because if mk is larger than 0, then mk is the maximum that we have there. Because the original definition of mk had the 0 in the maximum, but if it's larger than 0, you cannot have assumed the value 0, so it's the maximum of the rest indeed. So on this event, we can replace this by mk. So this is bigger or equal than the expectation of mk minus mk phi of omega, everything multiplied by the indicator. Okay, so we're almost there. Here we have something we'd like to remove this indicator function, but let's be careful. What happens on the complement of this event, right? If mk is smaller or equal to 0, then two things happen in the complement of this event. So of course mk is going to be exactly 0 because it cannot be negative. It's a maximum that has 0 in it. And mk composed with phi is always non-negative. So this means that the mk minus mk phi is non-positive. Or in other words, 0 is bigger or equal than the subtraction indicator. So I can always sum 0 here. And this is bigger or equal. Then let's repeat the first term. Expectation of mk minus mk phi, indicator mk larger than 0. And 0 is bigger or equal than, the expectation of the same thing indicator that mk is smaller or equal than 0. So we sum these two and we get the expectation of mk minus the expectation of mk of phi, which is very well known because phi is invariant with respect to p. So it doesn't matter if you take the expectation of mk or the expectation of mk composed with phi, this is going to give the same result, so this is 0. And you just prove that the expectation we want is larger than 0. So this finishes the proof of the lemma. As I said, the proof is quite obscure, but it works. And now we are fully ready to prove the main result. So let's go to the proof of the theorem. So first observation, note that we can assume that the expectation of x given I is 0. So the thing that I said, we are generalizing Birkhoff because now we are not assuming the measure is ergodic and getting the expectation in the end. We are not assuming anything and getting the conditional expectation of x given I. So this is actually not a big deal because once we observe that we can always assume that x has 0 expectation condition on the invariant measure, on the invariant sigma algebra, this is easy. Now, why can we assume that the conditional expectation is 0? Imagine that we are taking the average that comes in the theorem, k from 1 to n, 1 over n, and here we have x prime of phi k of omega. And imagine that x prime is given by x minus its expectation given I. But this expectation is of course also composed with phi k, right? Because this composition was before the sum. So if you're doing this, and of course everything summed, you see that the second term, this function here has to be measured with respect to the invariant sigma algebra. So it's an invariant function. So when we apply phi, we don't change anything. So this is equal to 1 over n sum minus the expectation of x given I. So the fact that this is invariant means that we can remove this from the average and put on the other hand, the other side. So we can indeed assume this to be 0, otherwise we just subtract it and this is going to appear the right way. So now what we're going to do is to show, so since we are assuming this, we have to prove that the limit of Sn over n is equal to 0 almost surely and in L1. This is what we have to prove, and we start by showing the almost sure convergence, and we start by considering the lim sup of Sn over n. This is going to define as x bar. We would like to show that this is 0, or that this is smaller or equal to 0, because then we're going to consider the lim inf, show that the lim inf is bigger or equal to 0, then the limit is 0. So how do we show this? We consider by contradiction that for some x epsilon bigger than 0, there is this event d epsilon defined as x bar bigger than 0, bigger than epsilon. And we're going to show that this event has probability 0. So if we show this for every epsilon, then we have proved that the lim sup is smaller or equal than 0 almost surely. Equivalently, we can show that the lim inf is bigger or equal than 0 almost surely. So we proved the almost sure convergence already. So that's our first step, show that the event d epsilon has probability 0. But an important observation is that d epsilon is invariant. Why? Because d epsilon is defined in terms of this lim sup. If we apply this not on omega but on phi of omega, we're going to remove the first term in the sum and add an extra term in the end. But this is divided by n, so this doesn't change the lim sup. So this is an invariant event. This is going to be essential during the proof. So what we are doing here is we're taking the state space S, and we have an orbit that starts in some omega, and we keep applying phi, and goes to phi omega, phi 2 omega, phi 3 omega, and so on. And we average x over this trajectory. But we just found a starting set, d epsilon, that if you start in this set, the lim sup is going to be bigger than epsilon. Not only that, we found an invariant set. This is the strangest part. We found an invariant set that if you start there, your lim sup is bigger than epsilon, even though your conditional expectation is 0. So this motivates the definition of what we call x star. So x star is defined as x minus epsilon on this event. Sorry, indicator of the epsilon. Why? Now we are building something that is just composing with something invariant. This is invariant. And we are starting on the epsilons where the lim sup is bigger than epsilon. So you're still getting a lim sup bigger than 0, even for this d star. So this is gonna, in the end, we're gonna bound the expectation of the lim sup, and this is gonna introduce a bound on the probability of the epsilon. So let's see how this plays. So we start with the same procedure as before. We define S star to be x star plus x star. You're composing phi, just like we did before. So this is the sum if we are measuring this instead along the orbit, and we define the maximum. Just as before, including the 0. S star 1, S star n. And you remember the event we had, m n larger than 0. This is the event that we had in the lemma, the maximum Ergodic Theorem lemma, this event here. We're going to give it a name. We're going to name it Fn. And we're also going to consider f, which is sum of this Fn occurred. And you're going to understand what this f actually is. So f means in the first observation, like sum of these maximums occurred, but they are increasing, right? The maximums always increase. So this is equal to the event where the supremum of S star n is larger than 0. Let's see this equality. If you are here in the union, you are in Fn for some n. So your maximum for that n is larger than 0. So it means that sum of this has to be larger than 0, because 0 cannot be larger than 0. So one of the s's have to be larger than 0. So the supremum is going to be larger than 0. Let's look at the other direction. Imagine that you are here. So it means if the supreme is larger, one of them is larger, so the maximum corresponding to that will have it, and it will be larger than 0. So Fn will have occurred, so the union has occurred. So this is an equality, and even more, we can now even divide by n here, and it's also an equality. Why? Because, okay, if this is bigger than 0, this is bigger than 0, but if you divide by n, it's still bigger than 0, and the other way around. And here we're recovering something that looks like what we had at the beginning, right? The limb soup. But what we're going to do now is to break this into its definition. So this is equal to the supremum over n of a big sum, right? It's x0 minus epsilon indicator of the epsilon plus same thing, x minus epsilon indicator of the epsilon, but now composed with phi n minus 1 of omega. And we take the average, we divide everything by n. This should be larger than 0. Just writing this beast here. And we're gonna separate the terms for the x's from the terms for the epsilon. And why? Because the x's is what we actually know something about, and the epsilon is gonna be the invariant part. So supremum of x0 plus x0 again, phi n minus 1 over n. So this we recognize, this is s again. And we have now minus epsilon goes out. And look at what we have. We have indicator of the composed with phi, indicator of the composed with phi square, until indicator of the composed with phi n minus 1. But the epsilon is invariant. So all of these are just the same. Get n times the indicator of the epsilon divided by n, so the n disappears. So this is what we have. By the way, I forgot here, this first term is also multiplied by the indicator of the epsilon, and here is a minus. Okay, so as I said, the first term we recognize, this is the sum Sn over n. And this indicator of the epsilon minus epsilon indicator of the epsilon larger than 0. Or if you prefer, I can put this on the left. Say this is larger than epsilon, indicator of the epsilon. Another way to write this is to say that the supremum over n is larger than epsilon and the epsilon occurred. Let's see the equality between these two events. So the event above, if we are in the event above, we cannot be outside of the epsilon, because then 0 is not going to be larger than 0, right? So 0 cannot be larger than 0. So if we are in the event above, we are in the epsilon. And if we are in the event above, and therefore we are in the epsilon, so the Sn has to be larger than epsilon. So here. Underneath is also clear. If we are in the event below, we are in the epsilon, so it doesn't matter that indicator is here. We can forget about it, and we get just what's below. Now, this is what's really interesting. The epsilon is the limb sup of Sn over n larger than 0. If the limb sup is larger than epsilon, then the sup is also larger than epsilon. So if we are in the epsilon, we are already here. So there is no reason to keep the first part. So we managed to make a long massage on this f and just prove that f is equal to the epsilon. What's the advantage of this? Because remember the lemma. The lemma told us that the expectation of x, any x, right, on the event indicator, right, of m star larger than 0 is larger or equal to 0. This we had. But this is equal to the expectation of x star indicator of Fn. So we know that the indicator of Fn, in the indicator of Fn, x star is larger or equal than 0 in expectation. So what's the importance of this? We're not there yet, but it's we're almost done, because just the intuition, remember that x star had this indicator function here. If the expectation is positive, we can try to show this, that this minus epsilon probability of dE is positive if it's not a contribution from x. So dE times something negative has to be positive, so dE has to be 0. Probability of dE has to be 0. But let's do this computation with care. So we know that 0 is smaller or equal than this, right? But remember that x is in L1, so that means that x star, which by the way is in absolute value bounded by this, also is in L1. So we can use, and remember that Fn, the union of Fn is F. So we can use the dominated convergence theorem to bound this, to say that this, the expectation of x star indicator of F, this is the limit of indicator of Fn, so you can take the limit out, and this is larger or equal to 0. So 0 is smaller or equal than the expectation of x star indicator not of Fn but F. But F, we just saw that this is D. Now, who is x star again? X star, you see it's becoming a bit redundant. X star is x minus epsilon indicator of D. But indicator of D is already here, so that's it. So this is the expectation of x indicator dE, the epsilon, minus epsilon probability of the epsilon. Now, I said, okay, x should not matter, so this should be bigger or equal to 0, so the probability of the epsilon should be 0. But why x should not matter is because x has conditional expectation with respect to I equal to 0, and the d epsilon is invariant, so it goes out of this conditional expectation. So now this is 0, so we realize that d has probability 0. Otherwise this would be strictly negative, not non-negative. So we've just proved that the lim sup of Sn over n is larger or equal to 0. Analogously, we proved that the lim inf of Sn over n is smaller or equal to 0. Sorry, the other way around. We just proved this is bigger or equal, smaller or equal to 0. This is bigger or equal to 0. So together we get the almost sure convergence. So now everything that's left is to prove that convergence also happens in L1. And the trick here is the same as we did before with martingales. We have our x, so we're going to just define x prime m to be a truncated version. So it's going to be x, but on the event that x smaller or equal to m. And just to facilitate our calculations, you're going to define this to be x minus x prime. So we have x is x prime plus x double prime. But the advantage is that x prime is bounded. So we know that, let's take the limit that we know to be sure, to be true. If we take x prime in the statement that we already proved, we get is almost sure convergence. Because x prime is just any decent random variable in L1. So we get is almost sure convergence. But these variables are uniformly bounded. So this convergence is also in L1. So this is good news for us. We get that the expectation of this difference is 0. Sorry, it goes to 0 with n. So now we have to correct, right? What happens to the x double prime? So let's look at the expectation of the same thing, but now when we put the double prime, which is the residual when we truncated x. So this we can, sorry, let's take the absolute value here. We can put the absolute value inside in the 1 over n. And here we have the expectation of x double prime phi k omega. And now the good part is that this is invariant, so taking the expectation composed with phi is not going to change anything, and this is an average, so this is just going to be the expectation of x double prime, which is, by the way, finite, right? X double prime is an indicator function times x, which is in L1. So x double prime is also in L1. So when we take the subtraction, so 1 over n sum of x double prime phi k minus the conditional expectation of double prime given I, this is going to be bounded by twice the expectation of x double prime. So here we can, you see, we can bound the first term like we did above by the expectation of x double prime, and the second term we can put the absolute value inside, so it's the expectation of a conditional expectation, which is just expectation. So here we have, when we take the prime guy subtracted from its conditional expectation, it goes to 0. The double prime guy doesn't go to 0, but it's bounded by something that's going to 0 with m, not with n, but with m. We know that by the dominated convergence theorem, we know that the expectation of xm double prime goes to 0. It's just taking an L1 variable and multiplying by something that's going to 0. And the expectation, by the same reason, the expectation of x prime m is going to the sorry. Here I don't want to bound the thing. I want the expectation, the conditional expectation given I. So this converges to the expectation of X given I. So now we just have to check all the boxes and, first choose M such that this is very close to the expectation of X, and even larger M such that this is very small, and then take N very large so that this is very small as well, and you get a 3 epsilon thing that is arbitrary. I'm not going to make all the details, but we have finally proved Birkhoff's theorem, which is, okay, it's a Thoth cookie, but in the end it took us, what, three pages perhaps. Okay, thank you and see you next time.